counting on the stuff we saw in the video, kind of conjure up some of those images, hopefully, the universe series that we saw, the lives of stars. I guess before I go to this slide, I'm going to put something on the board kind of not related to this slide. So before we got here, I think in this part, we talked about something that was like 8 solar masses, 8 times the mass of our sun. That's kind of the breaking point. Anything less than this we call low mass stars. This is kind of review of what we did last time. Anything above we call high mass stars. And before I do this slide, I want to remind you, when we talk about low mass stars, we said that basically, you know, our sun is a low mass star because our sun is 1 solar mass. Does that make sense? That's how massive our sun is. So our sun is a low mass star. We basically said, I kind of get my parts mixed up, but basically it starts as a main sequence star, okay, and then it goes to a giant. I think we talked about that. You can see it move on the HR diagram, okay, and then we said basically the giant is going to expel its planetary nebula, okay, and it's going to end up as a white dwarf. Just to kind of remind you what we're talking about, stars, okay? Cool. Well, now there is this low mass star. I only have one slide, and actually the video talked about these guys. It's another dwarf. Okay, we have white dwarfs here. Yeah? Actually, it's the red dwarf, a red dwarf. Okay, so if you go low mass stars, you're talking about basically something that's big enough to become a star. We said 0.08 solar masses. Okay, anything up to about 0.4 solar masses. Anything in this range, basically, it's going to be a red dwarf. It's kind of a finer point, but red dwarfs do a little bit something different. First off, they're very small, okay? And we said if something's very small, it like lives forever, okay? Like 100 billion years. Something that's about the 10th size of our sun. We looked at the end of the last chapter. So here's what red dwarfs do. Red dwarfs, you figure, they're not very dense. Okay, they're kind of a little bit fluffier. So matter can, what we say, convect. We've talked about convection in here before. Basically, convection is where hot stuff moves up, it cools down, and then it moves back down. Okay, so we basically have fresh hydrogen, we should say, we have helium convecting out and fresh hydrogen convecting in. This is an awesome thing. So basically, as it's a main sequence star, it kind of brings in fresh hydrogen, it expels its old helium. Okay, so it will actually end up with just basically an orb of helium. It will never do this giant stage. It will never go on and become a white dwarf. It's just going to be a red dwarf. Forever.
So that means it's basically in its, what's it called, main stage or whatever?
Main sequence stage.
Main sequence forever.
Forever. And we looked at some,
That's a long time.
yeah, like one of the last slides in the previous chapter, we said that if a star is about 1/10 the size of the sun, it's going to be a main sequence star for 100 billion with a B years. So
basically forever.
that's close enough to forever for
We
me.
literally know what happens to it at the end, because it hasn't occurred.
Well, things like the dwarfs, like this thing, and actually the white dwarf, all they do is they kind of cool down. So, you know, if you come back in 150 billion years, you know, after it's basically, now it's all helium. It has no fresh hydrogen to convect in. It's just going to be kind of this blob of cool or something. So right now it's a real star. It has nuclear fusion going on. Okay, but dwarfs kind of cool down. Yep, I think that is pretty darn cool. So like I said, this actually is kind of this would be your low mass. Low mass stars, okay? And this is your red dwarfs. I mean, it's just a little, it's kind of but remember the dude on the video said that most stars are these kind of M-type stars, these kind of light guys. So, all right. So now back to the normal things. All right, so we talked in this chapter already kind of about the low mass stars. Now we're going to talk about the high mass stars, the exciting stars. But the thing about high mass stars is, remember, they live their lives faster. Okay, they go through their chips faster, just like we saw in that video. So they start out the same way. Remember we talked about those giant molecular clouds, or the molecular clouds, the stellar nurseries, where a whole bunch of stars can be born at one time. Okay. They start out as a nubbin, a protostar, become a main sequence star, a full-fledged star. Okay, they will expand. This semester, I'm just saying kind of giants. I'm just like, because you have red giants, you have super red giants, you have super giants. I don't know. But just on an HR diagram, if you look for that kind of diagonal, that's main sequence. Kind of above that, that's your giant region. So these things are going to swell. Okay, but they're going to actually go on and do additional types of fusion. I said that they go through their chips a lot faster than the lower mass stars. They actually have another mechanism called the carbon, nitrogen, oxygen cycle to kind of speed up the fusion rate. Okay, so, yeah. So actually, carbon, it doesn't stop at carbon. Carbon is fused into heavier elements. But kind of like the video said, you remember the guy was in the foundry where he had kind of like molten metal behind him, and he said, iron, it's iron. So basically, when these massive stars end up with iron in their core, they're done. They can't do any more.
And how do we get uranium?
That is, I think it's called nucleosynthesis. It's coming up. Basically, when the star blows up, it releases more energy, and I think the video addressed this too. Yep, that actually provides crazy conditions for more nuclear fusion to happen. So that is amazing. Amazing. Yeah, so we get heavier and heavier elements. And so I put together this table because I kind of wanted to look at it this way. These are, and I want to emphasize the later fusing times. Okay, these are all as if the star, when it was a main sequence star, was 25 solar masses. Okay, so 25 solar masses, clearly a high mass star. Based upon the physics, we know that when it begins fusing carbon, carbon makes neon. How long will it do that? For 600 years. When it begins fusing neon, neon primarily makes oxygen for a year. When it begins fusing oxygen in the core, that will make silicon. How long will that last? 6 months. When it begins fusing silicon, bless you, it will form the main product is iron. And how long will that happen? 1 day. So you're like, wouldn't you like to see the countdown there? And actually, we're building up to a supernova event here. The thing will explode after that. So in the video, they talked about the kind of this onion sort of thing. So the way you read the onion or think of the onion is the core is the hottest, and the core is where you have your most sophisticated nuclear fusion going on, your heaviest things being made. This actually is right before it goes boom, because here we have, let's see, they're showing a core that is iron. So there's iron in that little center. So notice it's in a giant stage. That's kind of what they're trying to show you here. So this actually tries to show you why is iron such a tipping point. And as it turns out, we talked about 2 types of nuclear reactions. We talked about the fusion, which is what stars do. Okay, then we also talked about the fission. And actually fission is a nuclear reaction where it's breaking something apart. So uranium is great at fizzing. Uranium basically splits apart and creates energy that way. So iron would be more likely to split apart than to fuse together. I think that's one way to look at it. So these are actually showing you nuclei fusing together. So if you take a carbon plus an oxygen, the middle of the atom, you can actually get a nucleus that's like a silicon. You take 2 oxygen, you get sulfur. You take 2 silicon, of course, you get iron. That's kind of how we get an assortment of things there. This little thing, actually right here, notice in each of these cases, we have helium is the culprit, kind of fusing with something bigger, okay? And you recognize, you know, helium fusing with carbon gives you oxygen, helium fusing with oxygen gives you neon, helium fusing with neon gives you magnesium. So the thing about helium is that actually it adds 2 protons to whatever it's fusing to. So we do kind of have this trend in kind of relative abundance of the elements. For kind of the even elements, they tend to be more abundant, and that's because kind of they come in pairs if you fuse a helium. All right. So, iron core to supernova. It was fun coming up with some of these titles of these slides. So, basically, like this slide says and like the video said, ever since the star was an entity, gravity was trying to kind of compress it down, okay? And when it had energy, it was creating that energy, was trying to fluff it back out again. We said that our star is at hydrostatic equilibrium, so basically that's a wash. Gravity doesn't win out and the star's not expanding either. But it just kind of caught up with it, so that gravity catches up with it. It cannot create any more energy from fusing iron. So what happens in the iron core is something like this. You're actually seeing over there on the left, or excuse me, over here on the right, this is showing you a proton plus an electron, okay, goes to create a neutron. I know it's weird, but under great pressures and great temperatures, that's what happens. So you end up with an object in the core that used to be an iron core. Now it's basically just kind of a neutron sort of object. Well, that works for a minute, because then basically well, it works for a good while. Basically then the neutrons support the weight of the star to a certain extent. But if the neutrons can't support the weight of the star, basically those neutrons try to occupy the same chair. Remember, we looked at a figure the other day that had kind of playing musical chairs. We had a couple scenarios, lots of chairs, a few people, and then basically the same number of people, but you took the chairs away. Where are the people supposed to sit, sort of thing? That's what actually happens at some point, where the neutrons try to occupy the same space as the neutrons, okay, and they can't, okay? That actually forms what we call a black hole. Okay, so the pressure is making them come together and they can't occupy the same space, and it forms a black hole, which a black hole is actually kind of in a sense, a tear in the fabric of space and time. That's the way I think of it. Meanwhile, what's going on with regard to that instant in time when basically it no longer has any sort of fusion going on in its core, the stuff collapsing hits the brick wall, which is probably basically a neutron star, and it rebounds out, but there's still stuff coming in. So basically you have stuff going out and coming in at one time. And that actually creates the conditions that works well for these heavier elements, forming these heavier elements. And that's called nucleosynthesis. So how do we get this? And I keep looking over there for the periodic table. There's no periodic table over there. But how do we get all the elements that are heavier than iron? That's it. So when that happens, I've heard like, I don't know, half a minute maybe, 30 seconds, sort of the supernova event, the explosive event. And then what's left is either a neutron star or it's crushed all the way to the point of creating what we call a stellar black hole. One of those two objects. In the meantime, the guts basically of the star, this is an example of the guts of a star, okay? This is what we call a supernova remnant. In the middle there actually is, and I think we're going to pick on it as an example of a neutron star is in the middle there. Here's an example of a star going supernova. So notice the star here on the left, normal star. The star over here on the right, clearly something's going on. Okay. So, this actually is a pretty good slide. If we look down here on the bottom, we'll start there. That actually, these are the low mass, how a low mass star lives its life. Okay, I think early on we talked about kind of that little accretion disk and that kind of those energy jets that can come out. This would be a protostar. Okay, and then we have a main sequence star, MS for main sequence star, and here we have a giant. That's assuming it's not going to be a red dwarf. Then over here we have your planetary nebula. And if it's a low mass, here we have your WD for white dwarf. And then the high mass stars, kind of similar. Kind of just skip to about here. To me, it's very similar. You have a main sequence star. It kind of goes back and forth between a few things, but basically a main sequence star. And then over here, this is your, I'll put SN for supernova. Okay, and then what's left over here is either a neutron star, or a black hole, BH for black hole. And that's it. All right, so the last slide actually is kind of setting you up for something that's going to happen in the next chapter. So we said that most stars actually have a companion star, and that's actually what's being shown here. Some of us looked at the star in Perseus, kind of a red sort of star called Algol, and Algol actually kind of is a variable star. And so here we have, this is a lower mass. I'll put L for lower mass. And this is a higher mass. I'll put H for higher mass. And actually, the higher mass, as it swells, can go ahead and dump on the lower mass star. And now actually the lower mass picked up mass, and it's behaving differently. It's kind of the idea here. But it can share material. That's the big thing to emphasize here. So let's go ahead and do a few slides in the next part. Bizarre stellar graveyard. Dun dun dun. All right. So kind of picking up where we left off, a lot of the stuff will be very familiar. So like for instance, what is a white dwarf? A white dwarf actually, we said, is kind of the end stage of a low mass star. And I like how the guy on the video called it a retired star. So actually I have a few slides here, and the video talked about it too. A white dwarf can actually have a second life. But Sirius is the brightest star in the nighttime sky to us. It's got a magnitude of like -1.4, apparent magnitude. And there's a Sirius A and Sirius B. Sirius B actually is a companion star, and it is a white dwarf. So the thing about a white dwarf is it's pretty darn dense. And to kind of demonstrate, and I think the video talked about this, but if you were to bring a teaspoon of a white dwarf back on Earth and weigh it, it would weigh 15 tons. But a white dwarf is normal material in that if we look at normal atoms don't run into each other because basically the electron around each atom says, no, you don't. Okay, so the electrons separate the atoms. That's exactly what's happening with the white dwarf. It's very dense, but it's supported by what we call electron degeneracy. The smaller the white dwarf, actually, the more massive it is. And I know this kind of seems strange. I think the video might have talked about this. But basically, the more massive it is, it keeps its electron degeneracy continues, but basically just kind of squishes down, okay? And I think that's kind of what we ran into with Jupiter and Saturn a little bit. But the white dwarf can only be a certain size, a certain mass. One of the things, quantum mechanics is just basically how does matter behave on a small scale, on atomic, electron, and even smaller subatomic particle scale. So quantum mechanics say that if you squeeze atoms closer, you squeeze electrons closer, and they are going to go faster and faster the more dense you make the material. Well, if you make the material dense enough, then those electrons are approaching the speed of light, which it's called the cosmic, speed of light is the cosmic speed limit. Things can't go faster than the speed of light. You can approach the speed of light. So if a white dwarf's mass gets close to 1.4 times the mass of our sun, then that means that it's about ready to do something it can't do. Electrons cannot go faster than the speed of light. So that's kind of like a critical mass. They call that the Chandrasekhar limit. So 1.4 solar masses is the Chandrasekhar limit. Thou shalt not be more massive than 1.4 solar masses, white dwarf. So here we go. Here is kind of what we looked at with Algol, the star. We have, in this case, we have a retired white dwarf, and we have a companion that is living its life, and it's expanded to the point where it can have some mass transfer. So as the mass transfers, it kind of can give the object, if it's a white dwarf, a second life. So we'll be looking more at kind of mass transfers like this. But it's kind of similar to, I don't know if the video called it this, but it's kind of similar to if you pull the plug in your bathtub drain and you watch the water going down your drain, it kind of gets ready to go down and eventually goes down. It's kind of like a disc of material. They call that an accretion disc. In this case, basically, it's stuff that's funneling from the bloated red giant getting ready to contact the white dwarf. So there are different things that can happen in that accretion disc. One of the things about the accretion disk is that it can heat up. Basically, this matter is kind of falling all over itself, kind of like creating friction. And so we can actually kind of see this glowing, this accretion disk. So in this scenario, we have a retired white star, it's the blue one, or excuse me, retired white dwarf, it's the blue one. Then we have an expanded red giant. An event called a nova actually is one in which, I don't know if you can see this down here, this looks like it kind of blew up. With a nova, what happens is fresh hydrogen goes onto the white dwarf, which is really dense. That hydrogen actually, around the outside of the white dwarf, it gets compressed enough and hot enough to begin nuclear fusion, which is strange because you think, no, that just happens in the cores of stars. But it can actually happen on the accretion disk or on the surface of the white dwarf, in that fresh hydrogen that came from that companion. So we call that a nova. Now, you guys, are you sure Mrs. Snipes is not a supernova? So a nova is different than a supernova. So a nova is just this. A supernova, it entirely blows up. And the one we talked about, what entirely blows up is a massive star. Nova is this. So actually, nova can reoccur. But we can have another scenario, and it's called a supernova with this same, it's another outcome with the same scenario. In this, actually, the white dwarf gets dumped on, okay? Its mass, actually, think of this as that fresh hydrogen actually adds on to the mass of the white dwarf, okay, and makes it nearly that Chandrasekhar limit, that 1.4 solar masses. What happens with a supernova and a white dwarf and being dumped on by its companion is that actually in the core, it begins fusing carbon. Because remember what a white dwarf is? If I put a WD here, white dwarf. Okay, what a white dwarf is a retired star, and it's mostly C for carbon in the core. When it gets this fresh material, it can go ahead and increase pressure and temperature, and so it can begin fusing carbon into, can't remember what carbon fuses into. But that does not go well. It can do it for just momentarily. That fusion basically, it doesn't have any stuff outside of it to kind of cushion the energy that's going to be created. So basically it blows itself up. Darn drift. Okay, and so this is another type of supernova. Personally, I would have called it something else. Because now in this class we've talked about 2 supernovas. And that's not my problem, that's yours. Okay, so we have a supernova of a massive star blowing up, and then we have a supernova of a white dwarf blowing up. Yep. So, and I think I've gotten away from it, but the convention I learned it is to call this one a type 1A, and the other one, I'll put this an SN from massive star. Okay, I learned that as a type 2 supernova, so for what it's worth. But I think for the test and everything, like in my notes and everything, I've kind of changed it over to describe it more of what it is. A white dwarf supernova. Okay, it got dumped on to the point of beginning fusion again in its core, and it could not handle it. Okay, so a massive star supernova. Massive star supernova. That's what we talked about at the end of the last chapter. That was basically when the massive star had iron in its core and it could not fuse iron. Versus a white dwarf supernova. But like I said, they just should have given it a different name. And while they're at it, they should have called novas something other than novas. Because you know what I'm saying? I'm like, yeah. So anyway, just so you kind of hopefully see those two. And I don't think I have any test questions this semester over it, but there's a subtle difference between these 2 explosive events, and it's one of the differences is summarized here. What you're looking at is time in days for it basically to get dimmer, okay? And there's kind of a subtle difference in whether it was a supernova from a white dwarf blowing up or a supernova from a massive star blowing up. The other difference is you can tell by the hydrogen content. So you have to differentiate between those 2 types of supernova. The other thing you have to differentiate is for a white dwarf, these 2 events, novas and a white dwarf supernova. So one thing off the bat is supernova, when the white dwarf entirely blows up, are a lot more luminous, a lot more energy is released compared to a nova. And then the other thing about a nova, which isn't quite as crazy on the energy scale, the other thing about a nova is that it can reoccur. I think that's cool. The white dwarf is left intact to live again. Cool. Supernova, not so much. But a distinction between a supernova that comes from a white dwarf is when a supernova comes from a white dwarf, it doesn't leave a neutron star or a black hole. Basically, it just entirely blows up. Well, the next few slides kind of go together. I know it's early, but let's take a break because I really think we're going to get through this in one more segment, and then we'll call it, then you can go play Halo. So let's take a Let's take a 10-minute break, and then that will kind of break it up a little bit.